Angular momentum is what makes the skaters spin around faster when they pull in their arms. We have two kinds of momentum. Linear momentum, how hard it is to stop the thing if it's going straight, and angular momentum, how hard it is to stop it if it's going around in a circle. And if you squeeze up the circle, it spins faster because the same amount of momentum is in there.
It's like another way of measuring mass, almost.
Well, not quite. Angular momentum is a spin problem, not a mass problem. It's connected to mass. It's connected to mass. It's how fast things are spinning around.
Is the sun like 95% of the solar system in mass?
Oh no, it's more than that.
Well, it's
The mass of the sun,
where
the
the
mass of the
is,
sun is
yeah.
lots more than 90%. I think. I don't know how much it is. Probably 99% of the mass of the solar system is in the sun. But the angular momentum is only 1/50th of what we have in the.
So Jupiter and Saturn were formed before the
They
iron-rich planets?
came down with the sun, in my opinion. They came down with the sun, and they could not slow themselves down because they could not ionize the stuff in their neighborhoods. They had magnetic fields going around like that, but they had nothing to push. They had no electrical particles to push. And so they could not throw away their angular momentum like the sun did. The sun was hot enough to shine in the ultraviolet that knocks the electrons off all the particles, and then the magnetic activator can push them away. Yeah.
So the sun like grabbed the planets and are using them as its arms.
No, the sun didn't grab the planets. The planets were born by the sun. It didn't grab them from outside. It has no way to do that. If they came from outside, they would stay outside. If they were born with the sun, they stay with the sun. Families that pray together stay together. I'm sorry. But the things that are born in orbit around something else stay in orbit around that something else. And if they come from far away, they can't get caught. You can't get one astronomical object to catch another astronomical object without putting a retro rocket on it. Now, if something came by the sun, just as Jupiter came by behind it and slowed it down, then it could get caught. Otherwise, it couldn't get caught.
So it'd be moving a bit too fast.
What? Yes.
It'd be moving a
If
bit
it
too
came
fast.
from too far away, it cannot come in with less than escape velocity from the sun.
It still has the same momentum it arrived with, more or less.
Yeah.
You don't lose it, yeah.
When the comets come in around the sun, the closest they get to the sun is on the far side. They come from way out there, and the closest they get to the sun is on my side. And then they're falling while they're coming in, and they're coasting when they go away. All right, yeah.
If you heat up a magnet, doesn't it lose its...
Yeah. If you heat up a magnet, it loses its magnetic
So
field.
how come this magnetic egg beater have so much force if its
Well,
center is so
there's the sun. We know that the sun has a magnetic field. There's a little bit of a problem why it has a magnetic field, but I look at it this way. Protons are a lot heavier than electrons. So in the sun, and they're in a gas, you know, all the particles have to have the same amount of kinetic energy. So the electrons have to be going lots faster than the protons, because the protons weigh nearly 2,000 times more. So the electrons have to be moving much faster in the sun. So there must be a tendency for the sun to be negative on the outside and positive on the inside. And then if you spin it, you get a magnetic field, even if you didn't have any other reason. But we know that the sun has magnetic fields. The sunspots are magneto-hydrodynamic zits. They're places where the magnetic field comes onto the surface of the sun. So we know that the sun has a magnetic field. Exactly why it has a magnetic field, I can't answer you, but we do know that kind of thing. And also this other difficulty, when you stir an electrical conductor in a magnetic field, it has very peculiar behavior. It's called magneto-hydrodynamic behavior. That's why I call them magneto-hydrodynamic zits. If you stir mercury in the beaker, it will stir fine. You may have to push the spoon in, because the spoon floats. Okay, the spoon will float in mercury, so you have to push it down, but you can stir it, and it'll stir okay. If you put a magnetic field through it, it will not stir okay. And the disturbance in the bottom will come squirting right out to the top. And that has only one name, it's called magneto-hydrodynamic problem. And the sun has that kind of problems. When it tries to move around, when the gas is trying to move around in the magnetic field, there are all these complications. It's not simple at all. The sun is very much more complicated because of that, because of these magnetohydrodynamic problems. Whenever you try to move an electrical conductor through a magnetic field, it drags the magnetic field with it. Now what we know about the sun is that the equator is going around faster than the polar regions. That's to say, it goes around in a shorter number of days than the polar regions go around. So that drags the magnetic field into these long loops. And after 11 years, it's so dragged out that it starts buckling through the surface like sea snakes, and we have a rash of spots. Then it seems that they short each other out and start over again. 45 degrees away from the polar regions, they start. For 11 years, north spots lead in the north and south spots lead in the south. Next 11 years, north spots lead in the south and south spots lead in the north. It's really a 22-year cycle. But exactly why it works like this and exactly why it flips over like this, I don't think anybody really knows all this yet. But the sun is a real messy affair. It's not a solid thing like the earth, so that this thing stays where it is most of the time. Just once in a while it blows up. On the sun, it's not like that. Wow, what time is it? Have we got time to do space and time?
It's up to
Quarter
them.
after 9.
It's a 9:15. It's up
We
to
got
them.
3/4 of an hour. Well, we can go on with the
Well,
planetary system if you want.
9:15, that means it's been 3 hours. But if,
Oh, we're supposed to be dismissed
but
already.
if they want to stay, I'm willing.
It's ice cream time.
If they want to stay, I'm
No,
willing.
we can start tomorrow on space and time if you want. But now we're up to the interesting things. In my opinion, all this stuff is dull, boring stuff because it's just classical physics and you can figure it all out if you work at it real hard. And, but the question of what is space and what is time, that's a much more tricky question. And the relationship between space and time is a much more interesting thing. So we've talked about now about the actors in our drama. The actors in our drama are hydrogen atoms. And we've talked about the name of the play. The name of the play is Folly. To a first approximation, the universe is hydrogen gas falling together by gravity to galaxies and stars. To a first approximation, that's what we have. But now we have to talk about the theater and the date. The theater is space, and the date is time. We have to find out what space is. We have to find out what time is. If we can possibly do that, I want you to see if you can word for yourselves what space is, what time is, what the nature of those things is, and what the relationship between them is, if you can.
Are
Yes.
you going to talk about the beach tomorrow?
About what?
The beach?
Beach? No. Why should I talk about the beach tomorrow? We're nowhere near there yet. Nowhere near yet.
Okay, just curious.
But you see, there are two essential questions which face us as a species. How did the universe get like that? And how did we get like this so we can worry about how that got like that? So we do have to talk about that. How come the chimpanzees, they never come to these classes. So something happened to us that didn't happen to the chimpanzees, and something happened to the women that didn't happen to the men. Men were invented by women, and women were invented by men. We get what we asked for. Anyway, so that's one of the problems that we have to face. That's one of the problems that we have to face. How did we get like this? But we're not finished with how the universe got like that. We've talked about the actors, and we've talked about the action in the play, but we have not yet talked about the theater and the date. We do have to talk about the theater and the date, and that will turn out to be lots more interesting than all this junk we've been talking about for 2 nights. Lots more interesting, and lots more inspiring also. It is shockingly different than you thought. The universe is shockingly more interesting than it looks on the surface. So I guess now it's ice cream time.
Did everybody sign the book today that is here? No. Who did? Oh, no.
Excuse me.
have my, I know time is a measure.
Yeah, it would be good. And movements to the stage.
John Dobson.
Now, last time we had this difficulty, and so I think tonight we have to start all over. Let's see, where did I start? Up here. So I think we have to start all over tonight, because I've probably assumed that people knew things that they didn't know. So I brought a nice picture for tonight. If you don't like it, you're fired.
But you need us now. Now we know you need us.
Okay, this is the picture I want you to see.
What does the caption say, John?
I think it says, hang on.
Oh, where? Here.
It says Castle in the Pyrenees. And it gives the name of the artist. Anyway. But apparently that gentleman last night really thought that matter floats in space. So I have to wonder, you see, what kind of background you people really do have. I have just assumed that you all went to high school and have some sense of proportion. But sometimes I overestimate what sense of proportion people have. And so I think it might be smart to go back a little ways. So I've brought this nice book. This is from the Feynman Lectures on physics. And this is just a few of those things. But he has a nice statement here. If in some cataclysm all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world, if just a little imagination and thinking are applied. Now, I think that's very lovely. Did you ever worry about that? If we were all to die, what piece of information you'd pass on to the next critters? Now you see, it took us a long time to find out that matter is made out of atoms. Not really. Such a nice, simple thing. We people have lived on this planet for a few million years without knowing any such thing. Now you remember some of the old Greeks used to speculate about this, and they had all kinds of theories about this. Anyway, so we have a lot more information about it now. Now I want to read you some other things from this book. Don't sit on that, please. That was page 4, and next is page 27. 27. He's talking about the physics before 1920. Before 1920, our world picture was something like this. The stage on which the universe goes is the three-dimensional space of geometry as described by Euclid, and things change in a medium called time. This is our theater and our date. The elements on the stage are particles. Now for us it was hydrogen atom, but it's made out of particles, you see. For example, the atoms, which have some properties. First, the property of inertia. If a particle is moving, it keeps on moving in the same direction unless forces act upon it. The second element then is forces, which were then thought to be of two varieties. First, an enormously complicated, detailed kind of interaction force is electricity and magnetism. The other force that was known was a long-range interaction, a smooth and quiet attraction, which varied inversely as the square of the distance and was called gravitation. This law was known and was very simple. Why things remain in motion when they are moving, or why there is a law of gravitation, was of course not known. Now you see, he's very polite. You know, mostly if you read a physics book, you get the impression that the physicist knew everything. He never does it that way. He tells you very clearly in italics what we don't know. Now, what's the next one? On page 71. You have to memorize all these pages. Page 71. Here we are. Now, we've been talking some about matter in this class, and we've been talking some about energy. Now, this is Feynman on energy. We've been talking about the conservation laws and things. It is important to realize that in physics today, we have no knowledge of what energy is. Now I think I can read you some more out of time. Now I can read you page 4 of a different book called QED. QED means quantum electrodynamics. And I have to tell you a story also. Years ago, I was in Oregon. I was scheduled to give a slideshow at Da Vinci Days. In Corvallis, Oregon, they celebrate science and art on the same program for one weekend, and it's called Da Vinci Days. And so I was there from the beginning, and this is several years later, and I was asked to give a slideshow, but I read this to them first and asked them whether they wanted to talk about some of these interesting things or whether they wanted to see these dumb pictures. They chose to do this. So we called it Origins. That is to say, what happened to us that didn't happen to the chimps, so we could worry about how that got like that. Those two questions. And Oregon Public Radio recorded that and have played it many times in Oregon, and it's the most popular thing that Oregon Public Radio ever did. And when they play it, I get phone calls and letters in San Francisco. Anyway, so this is what I read to them. Physics has a history of synthesizing many phenomena into a few theories. For instance, in the early days, there were the phenomena of motion and phenomena of heat. There were phenomena of sound, of light, and of gravity. But it was soon discovered after Sir Isaac Newton explained the laws of motion that some of these apparently different things were aspects of the same thing. For example, the phenomena of sound could be completely understood as the motion of atoms in the air. So sound was no longer considered something in addition to motion. It was also discovered that heat phenomena are easily understandable from the laws of motion. In this way, great globs of physics theory were synthesized into a simplified theory. The theory of gravitation, on the other hand, was not understandable from the laws of motion, and even today it stands isolated from the other theories. Gravitation is, so far, not understandable in terms of other phenomena. After the synthesis of the phenomena of motion, sound, and heat, there was the discovery of a number of phenomena that we call electrical and magnetic. In 1873, these phenomena were synthesized with the phenomena of light and optics into a single theory by James Clerk Maxwell, who proposed that light is an electromagnetic wave. So at that stage, there were the laws of motion, the laws of electricity and magnetism, and the laws of gravity. I'm going to read you that last sentence again, and I'm going to interpose. So at that stage, there were the laws of Newton's laws of motion, which take inertia for granted. The laws of electricity and magnetism, which take electricity for granted. And the laws of gravity, which take gravity for granted. See, Einstein's special theory takes space and time for granted. General theory of relativity takes gravity for granted. Newton's laws of motion take inertia for granted. Quantum electrodynamics takes electricity for granted, takes Heisenberg's uncertainty principle for granted, takes Pauli's for granted. There's nothing else to take for granted. We've taken the whole damn thing for granted. I'm not willing to do it. I am not willing to take any of this junk for granted. And you guys aren't going to be able to either. You're going to have to understand all these things. You're going to have to understand what energy is. Just because they don't understand this at Caltech does not intimidate me. Attempts to understand, well anyway, let me go on. Around 1900, a theory was developed to explain what matter was. It was called the electron theory of matter, and it said that there were little charged particles inside of atoms. This theory evolved gradually to include a heavy nucleus with electrons going around it. Attempts to understand the motion of the electrons going around the nucleus by using mechanical laws, analogous to the way Newton used the laws of motion to figure out how the Earth went around the sun, were a real failure. All kinds of predictions came out wrong. Incidentally, the theory of relativity, which you all understand to be a great revolution in physics, was also developed at about that time. But compared to this discovery that Newton's laws of motion were quite wrong in atoms, the theory of relativity was only a minor modification. Working out another system to replace Newton's laws took a long time because phenomena at the atomic level were quite strange. One had to lose one's common sense in order to perceive what was happening at the atomic level. Finally, in 1926, an uncommon sensing theory was developed to explain the new type of behavior of electrons in matter. It looked cockeyed, but in reality, it was not. It was called the theory of quantum mechanics. The word quantum refers to this peculiar aspect of nature that goes against common sense. It is this aspect that I'm going to tell you about. Well, we're not going to do that right now, but I have to clue you in that there's some things that I more or less have taken for granted that you know, and it turned out last time that I had taken too much for granted, and so I don't know. So if there's some of these fundamental things that some of you don't know about, like that matter is made of electrical particles, please mention it. Remember at the very beginning we asked what's the universe made of, and it's made out of hydrogen, primarily out of hydrogen. But the hydrogen is made of electricity. See, we left out the interesting things. We left out the fact that the hydrogen is made of electricity. We left out the fact that it falls together by gravity. And we left out the fact that when it's moving it ghosts. We left out all the interesting stuff because I just wanted to start with our feet on the ground. But you see, I'm not sure that everybody understands that we got into a war, you see, with that gentleman last night. He's not here tonight, is he?
He's working, he couldn't come.
I was hoping he would come.
He'll be back, he had to work and long hours.
Okay. So if there are any questions about this fundamental stuff, please raise it now. I don't like to take for granted that you people know things that you don't know. But you see, knowledge is a funny thing. You have a certain number of cubby holes you see in your mind. And so you fit things in. Oh, this one belongs over here, this one belongs over here. And I'm reminded of a story that I once read. There was this station master in some small town, and he had a broken package on the train, and it contained a turtle. Well, he'd never seen a turtle. And he looked at it, he's got to make a report. This broken package is on the train. So he says, it's not a dog, and it's not a cat. It must be an insect. He doesn't have enough cubby holes. Doesn't have enough cubby holes. Now, if you don't have enough cubby holes, you're really screwed. You really can't handle this stuff. So that's what I have to find out. I really don't know what state you people are in. Anyway, tonight we want to talk. Is it okay to go on, or do we need to talk about some of these things?
What did you mean a while ago when you said that hydrogen is something or other related to electricity? And is that
Made of electricity.
made of?
What is hydrogen atom made of? One proton, one electron. What are they made of? They're made of electricity. We'll get to all that little by gradually, and not so little and not so gradually. But the curious thing is, you see, well, when I was a little kid, 10 years old, I used to wonder, if I had the universe to make, out of what would I make it? I'm not sure. Do all kids think like this?
Sometimes about the world.
Yeah.
What I make.
Anyway, how old are you?
11.
11. You're already too old. When I was 10, I used to worry, you see, if I had a universe to make, out of what would I make it? And it never would have crossed my mind to make it out of electricity. I know now how to do it from scratch. You'll all know before you get out of here how to do it from scratch. But you'll have to do it, you'll have to make it out of electricity and gravity. Anyway, you'll see. It'll all be perfectly clear after a while. And I also used to wonder, suppose there had never been any universe. And in those days, I took for granted that there'd be this big, black, empty space in time. Now, we don't think like that anymore. The way they think now is that matter is wound up against space-time, and space-time is wound up against matter. The way they say it now is that matter tells space-time how to bend, and space-time tells matter how to move. So they're all part of the same thing. Anyway, we'll get to all that.
Can you repeat this once more?
What?
Can you repeat this once more?
Which part?
The whole thing?
The last couple.
Because it was so quick, I couldn't like follow all the steps.
Well, I used to think when I was a little kid that if there hadn't been any universe, there would still be space and there would still be time, but they'd be empty. But I don't think like that anymore, and the physicists don't think like that anymore either. The way they put it is that matter tells space-time how to bend. The gravitational field, the electrical field, the magnetic field, they tell matter how to go. And so matter tells space-time how to bend, and space-time tells matter how to move. So if we didn't have the particles to wound up
Space-time tells
space-time,
how to move. You mean time tells how to move?
space and time together tell matter what to do, yeah. We'll get to it, don't worry about it yet. Don't worry about it yet. Tonight we have to first ask what is space and what is time. Remember that was the homework. What is space and what is time? What's the relationship between space and time, if there is one? First of all, how many think there is one? Please put up your hands. Oh, pretty good. Some of you are pretty slow at getting it up, though. All right. I want to know if any of you can make a suggestion as to what space is as you understand it, and what time is as you understand it. Either one of them, I don't care which one you work at. Make a suggestion. You've all lived in this world a number of years. Even you've lived 11 years here.
Time is made by man.
What?
Time is made by man.
No, clocks are made by man.
Right and silent. We're timekeepers.
What? We make timekeepers. We make timekeepers, and they keep the time. But we don't make time. What makes you think we make time?
Or we make the
None of these,
relation
you look
time.
on all these storefronts, you won't find any of them. The time house. What? The space house on one side and the time house on the other side. Then the electricity house, the gravity house. Now you know, years ago somebody sent me from Hollywood an advertisement by a company, you see, that makes gravity. They say, you've been taking it for granted all these years, and you never even did find out that we've been making gravity all these years without recognition. Anyway, I didn't keep it. All right, so what is space and what is time, please? Come on. I don't care whether you're right or wrong, or whether it's silly or not silly.
Space is the distance between two objects.
All right, then what's time?
Yeah, I did like
Time is a measurement.
Get from there
What?
to
It's a
there.
measurement.
That is how long it takes between one and another. Now, there was a graffiti in the men's room in the Pecan Street Cafe in Austin, Texas, which said, time is nature's way of keeping everything from happening at once. So then space is nature's way of keeping everything from happening in the same place. Okay? So that much we can do easily. Now, how many of you think there's a relation? Well, quite a few of you think there's a relationship between space and time. What is it, please?
Do they define each other? I mean,
Space defines time and time defines space. How many agree with him? Well, you've got two followers. Get some names.
Fiddle.
All right. All right. Those of you who think that there's a relationship between space and time, what do you think it is? What is the relationship between space and time?
The more time you need to get from one point to another, the bigger is the space in between.
Okay. As you say, Nelson is 3/4 of an hour from here, whatever it is.
Yes?
That's how we do it. Yeah. However, there's really another interesting thing about space and time. Einstein noticed, well, let me go back a little. Einstein was a very cool-headed physicist when he was 26 years old, about 1905. And he had this problem in electrodynamics, and he looked at it very carefully, and he thought, this part of the problem we understand perfectly well. We could not have made a mistake there. And this other part of the problem we understand perfectly well. We couldn't have made a mistake over there. So the only other place we could have made a mistake is our understanding of space and time. And so he rethought space and time. And what he knew was that space measurements are not objective. You might say that you know how far it is from here to Nelson. But how far it is from here to Nelson is not an objective distance. An astronaut going by in the spaceship at a very high speed will not agree with you on how far it is from here to Nelson. And he will not agree with you on how long it takes your clock to go from 8 to 9. His clock does not go from 8 to 9 at the same rate that yours goes from 8 to 9. Now, is that clear to you, all of you? Probably not.
You mean, is it now?
Well, you see, we take for granted that it's all perfectly straightforward like this and the world is objective. Well, it's not. There is no such thing as a distance, and there is no such thing as a length of time. That is to say, that everybody agrees on. Two observers moving with respect to each other disagree on how long the distances are and how long the lengths of time are. Well, anyway, let's do a little geometry on the board. Some of this you're all familiar with, I'm sure. If we have this nice triangle, and suppose we'll call this one X, and we'll call this one Y, and we'll call this one D, and we want to know how big D is if we already know X and Y. You all know how to do this. Does anybody not know how to do this? All right, get over here then. If we make a square out here, okay, make a square out there, and make a square down here, and make a square out here, which we don't have room to, then these two, when added together, make that one. And the way we write that is that b squared equals x squared plus y squared. Okay? This is a square, this is a square, and this is a square. And this one has the same size as these two added together. That's okay. Now you can sit if you want. Now, we can take the square root of this thing. We can take the square root of this thing. The square root of d squared, of course, is just d. So d equals the square root of x squared plus y squared. Now, this is a cheater. See this little gadget here? That's a cheater. We have no idea how to take the square root of x squared plus y squared. This just said that we did. Do you follow me? We didn't take it. We just said that we did. All right. Now, the difficulty is, well, let me ask you, for whom is this an okay equation? For you? No, no. This is an okay equation for flatworms which have died. If they're not going to come out of the plane of the board, and they're not going to move with respect to each other, this is an okay equation. Now, if we're 3D people, and we want to know the distance from that corner down to this corner, then we have to square that one, and square that one and add them together. That gives us this one squared. Leave it squared. Then we add the one up the wall squared. This one squared, leave it squared, plus that one squared gives us the one down the diagonal. So then we have to add that other thing in here, plus z squared. And that gives us the one this way, see? Einstein says that's still not good enough. We still have the problem that it's not objective to somebody going by at a high speed. He still will not agree with this on that. So he says we have to put time into this equation. So instead of having the distance between that corner and this corner, we have the explosion of a firecracker at that corner, called there then, and the explosion of a firecracker here now. So now we have to find the total separation between there then and here now. Got it? So here to there, we've got here. Now how does time come into this? We've got to put time into this thing. How does time come in? Go ahead, speak up.
No, I just saw a problem. I didn't see an answer.
Come on, how do you put time in here?
Well, it's squared.
It's going to be squared. It's going to go under the roof, above the roof, below the roof, over here, where? It's going to be squared. Under the roof? T squared. T squared. What are we going to put in here? A multiplication sign, a division sign, a plus sign, or a minus sign? Come on.
Divide.
It's a minus sign. Now, we can no longer call this for d, for distance. This is no longer d for distance. This is now s for separation, because now we're talking about the total separation in space and time between here now and there then. Got it? And this is objective for all comers. This is the same for all observers, from wherever they look and however fast they're moving, or in whatever direction. Now, Einstein did not want relativity theory called relativity theory. He wanted it called the theory of invariance. That is to say, this is the same for all observers. They disagree on this, they disagree on this, they disagree on this, and they disagree on this, but they all agree on this. All right, let me do another thing. Now, suppose you were to take a picture of this book from where you sit, and she took a picture of it from where she sits, and her picture this time would be long, and this one would be short. And in your picture, this one would be long, and that one would be short. All right. I'll quiz you. You guys are up for a quiz. Uh-oh. What's the handle? That's not what I want. See, I used to have a whole lot of books that I carried with me, but I'm so far from home I can't carry all those books. So I copied some things off. So I think, first I think I'll do this one. This one? No, not that one. Let me see what I can get for you. Yeah. First I'll show you the pictures. And I'm going to read to you. He's talking about different observers and they're moving and they're looking at something. And then he says, in some cases the projection shows more of space and less of time. In other cases, the reverse is true. Is that right or wrong?
Right?
Well, first, we'll simplify this. We don't have to have it so stupid. We don't have to be like the physicists who are going to go all around the room on the floor and then up to the corner. We're going to go straight from this corner to that corner, call that x. To hell with the y and the z. Okay? We don't have to have all those y's and z's in here. So we'll erase it and make it a lot shorter. And just put our minus t squared in here. And now you can see what the problem is. So now the question is that correct? For one of the observers sees more space between the two events and less time. The other one sees more time and less space. Is that right or wrong?
Right.
How many agree with him that it's right? Put up your hands. How many think it's wrong? Please put up your hands. Come on, somebody put up your hands. Thank you. It's wrong. You have a plus sign in your equation. Remember when we did this with the book? Yours is this one long and yours is that one long? In order to find this thing, you see, you square this one and add it to the square of that one. But here we got to subtract it, not add it. The one who sees more space between the two events sees more time, and the one who sees less space sees less time. So you got to shape up. Pay attention. There's a minus sign in this equation. Time is anti-space. It is not another dimension of space. It is the opposite of space. Space and time are a pair of opposites. Now in this one, what has to be true for this to be zero? This has to be zero and this has to be zero in order for this to be zero. What has to be true here about these, that this should be zero? They only have to be equal. You do see there's a big difference here. Here they both have to go to zero in order for this to go to zero. And here they do not have to go to zero for this to go to zero. They have only to be equal. Now the interesting thing is that they're equal if a light beam can get from one event to the other. If a light beam can get from one event to the other, they are not really separated in space-time. They may have a space separation, they may have a time separation, but those aren't real. The real separation goes to zero. Now, when I was at the university, we used to make fun of the physicists, that on Monday, Wednesday, and Friday they believe in the wave theory of light, and on Tuesdays, Thursdays, and Saturdays they believe in the corpuscular theory of light, and on Sundays they contemplated at church. The problem goes away as soon as you look at this four-dimensional geometry. If a light beam can get from this event to this event, then the space separation is equal to the time separation between those two events, and they're adjacent in space-time. Now, the very spooky thing about this whole thing is that we all have come to the conclusion that the universe is out there, an indy-goddamn pendant of us, and the equation says no. The equation says that every event that you have seen away from you in space, you have seen backwards in time by exactly the right amount, so that the separation between you and what you saw was zero. Now, I have a friend in the Bay Area, down near San Francisco. He says, you have to be careful when you talk to these people. You have to tell them, this is Einstein's craziness, or this is Heisenberg's craziness. You're crazy enough. This is Einstein's craziness. I had nothing to do with it. And it's very old. It's been around since 1905. We've had plenty of time to get used to it, and I've so far found only one physicist who takes this equation the way it's written. Now, we were talking the other night that there isn't any such thing as radiation. Don't you see? There's no such thing as radiation. Between the emission event and the absorption event, there is zero separation in space-time. And it's no wonder that nobody ever caught any photons. You can wave your butterfly around. You can even do it out in the sun, you won't catch anything. There's nothing to catch. The equations say that there's nothing to catch. Now, the academic community has not taken it the way it's written. Einstein himself didn't take it the way he wrote it. He said the only thing we can understand by this zero is that a light beam can get from one event to the other in vacuo. But the equation says it's zero, and I take it as zero. Now, if you don't take it as zero, your physics will wash up the beach. You will not be able to straighten out your physics unless you take the equations the way they are written. and not the way somebody's gut says they should have been. You know, I always say something about our guts. Don't trust your guts, they're full of shit. So far, nobody ever called me on it. Let him who is without sin cast the first stone. Anyway, you do have to be careful about that. What's that?
Did you say pass the first stone?
Well, I think we're going to leave this for a little while, but I don't want you to forget it. And Einstein, when he came up with this notion, he had to investigate something else. What's Einstein's famous equation? This isn't his famous one. What's his famous equation?
E equals mc squared.
And there isn't really any c squared in it. I'll tell you why not, but there isn't any c squared in there. Oh, I could read this from Einstein if I can find him fast enough. Nope, not that one. Not that one. Here it is. Einstein, 138. No. Oh dear, this takes too long. It's too hard when I don't have those books. It's too hard. It's too hard. Nuts to it. Anyway, let me tell you what happened. This was put in the appendix to the relativity paper in 1905. Now, it was suggested 10 years earlier by Swami Vivekananda, who represented Hinduism in the Parliament of Religions in 1893. He met Nikola Tesla in Sarah Bernhardt's party. Sarah Bernhardt knew all the big shots. She gave these parties for all the big shots of her day. And so, in one of these parties, Swami Vivekananda was invited and he met Nikola Tesla, and he asked him, can you show that what we call matter is just potential energy? Now, Tesla did not get it shown, but Swami Vivekananda, in one of his letters, he writes, I have to go next week to get this new mathematical demonstration. Apparently it didn't come, but I met a young man in Tasmania last September, and he said that he's descended from Tesla's brother. And he said, we have it in the family archives that Einstein's first wife, Mileva Einstein, was a close friend of Nikola Tesla. And she wrote the papers in 1905. So she probably knew the problem from Tesla and brought it to Einstein. Now, by 1905, all the information was in Einstein's hands. He has written the quantum mechanical paper, and he knows that the energy of the radiation is related to the color. If it's redder, it's less energetic. If it's bluer, it's more energetic. That light comes in little packages, and the color tells you how much package they do, how big the package is, not something else. Turning the light brighter does not increase the energy of the packages. Changing the color increases the, bluing the color changes the energy of the packages. So Einstein knew by that time that light is coming in little bunches like that, which they are calling now photons. That was invented by a professor of physics at the University of California in Berkeley. That is to say, the word was photons. But Einstein knew that, and he also knew that if something is going away, the energy is redshift. Did you all understand this? We've talked about redshift? Ah, right. A detour. You all know about fire engines. When they're coming toward you, the bell is at a high pitch, and when it goes away, it has a low pitch. Ding, 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 ding. It goes away at a low pitch. The reason it slurs like that is because the fire engine missed you. You can tell by the length of the slur how far it missed you. All right. Now, radiation does the same sort of thing. A star coming toward you has all the spectral lines too blue. That's like a high pitch. Going away, they're too red. That's like a low pitch. So if a star went by you, you'd see blue coming toward you, and as it passed you, you'd get red going away. Okay? Now, it's not due to how far away it is. It's due to how fast it's going away. And the blueness is not due to how far away it is. It's due to how fast it's coming toward you. These are related to how fast it's coming toward you and how fast it's going away. All right. Einstein knew in 1905 that if something is going away, the energy of the radiation is redshifted and therefore lowered. And he's got a number on it. He also knew from his relativity paper that if something is going away, the mass is lowered. It's easier to shake if it's going away. It's hard to shake it while it's going away, but you have to understand. You have to understand this. If it's going away, as the mass is seen by you is lowered, and if it's coming toward you, the mass is increased. Now, and that's the same number. So probably Mileva, having put it in the appendix, E equals mc squared. Now, the reason the c squared is in there is to clean up the units. Einstein and I were raised in the same, more or less, in the same time span, where the units were centimeter, grams, and seconds. It was the CGS units, centimeters, grams, and seconds. Centimeter was the unit of distance, now it's the meter. And the gram was the unit of mass, and now it's the spilled kilogram. We've decided the universe is too big for centimeters and too heavy for grams. So we've changed it a little bit. But we still stick to those stupid things called seconds. We're so provincial. I shouldn't say that in Canada. We're so statey. See, we use that word down there, provincial. We're not insulting you guys. But I have to be careful when I come up here. Because you guys actually have provinces. Well, anyway. So what we had to do when we found out that energy and matter are the same thing, we had to find out how many units of energy made one unit of matter, of mass. And that's what the c squared is for. In Einstein's day and in my day, the speed of light was 3 times 10 to the 10th centimeters per second. 3 times 10 to the 10th centimeters per second. And the unit for energy was the erg, and the unit for mass was the gram, and we had to know how many ergs makes a gram. So the speed of light, c, is 3 times 10 to the 10th. What is it when you square it? 9 times 10 to the 20th. Now, the gram is the energy of an atomic bomb. And the erg is the kinetic energy of a 2-gram beetle walking 1 centimeter per second. And what that c squared in there means is that carefully handled, the kinetic energy of 9 times 10 to the 20th, 2-gram beetles walking 1 centimeter per second would vaporize Berkeley. But that's all the c squared is in there for, to tell you how many ergs makes a gram. It's not in there, really. What he said is what we call matter is just potential energy. Just like Swami Vivekananda wanted Tesla to show it 10 years earlier. So now you have to understand that matter dropped out of the physics in 1905. All that's left is energy. Matter dropped out of the physics in 1905. Now, if all this stuff that we see is just potential energy, you have to tell me what kind. What kind of energy winds this stuff up to the tune of 500 atom bombs per pound?
Electrical?
Well, that's pretty good. That's pretty good. How do you wind up against electricity? You get 20 points on that. How do you wind things up against electricity? Come here. push things that don't like each other together.
Gravity sucks, electricity pushes.
Electricity pushes. So you push them together. You wind up against electricity by pushing things together that don't want to be together. But there's what other way do we wind things up? All right, we're going to have a detour. We're going to have a detour. We're going to have two identical spring-wound watches. Pocket watches, not wrist watches. Pocket watches. We don't want to be fobs. Pocket watches, two spring-wound pocket watches. They're identical. And they're wound, one of them is wound up tight. The other one is totally unwound. They're both broken in exactly the same way so they won't run. Which one is heavier?
Totally wound up one.
The wound up one, because we put more energy in it, and energy is the only thing in this universe that's hard to shake. Energy is the only thing in the universe which is hard to shake. All right? Now we're going to dissolve our two watches in equal beakers of acid. What's the difference when they're dissolved? What?
Temperature.
One of them is going to be warmer. Which one? The one is going to be warmer. Now warmer means the particles are moving faster. That is to say they have more kinetic energy. And this time your extra energy is the kinetic energy. Your extra weight is the weight of the kinetic energy. Do you see? Works out perfectly straight. A pitched baseball weighs more than an unpitched baseball. Got it? If you're going to get out of here sane, you're going to have to think straight. You're going to have to think straight. It's perfectly straightforward, but don't fall into any holes. It's perfectly straightforward. What we call matter has disappeared from the physics. It's just energy. Energy is what's hard to shake. So if we got a wound watch that weighs more than the unwound one, now we have to talk about cuckoo clocks. How do you wind up a cuckoo clock? What? You raise the weights. That is to say, you wind up a cuckoo clock by raising its center of gravity in the gravitational field. Okay? So if I put it on a higher shelf, I wound it up more. Well, I have. You can laugh if you want.
Wouldn't the weight actually be lighter?
The weight would, but the hardness to shake gets more.
Oh, it's perfect.
All right, now we're going to have another detour. We're going to have paint shakers, one here and one on the moon. And we're going to have your power company agree to supply power on the moon at the same rate it does in Kaslo. And we have two identical paint shakers and two identical gallons of white boy once over white. No, Dutch boy once over white. Dutch boy once over white, and it weighs 6 pounds on Earth. How much does it weigh on the moon? 1 pound. And we're going to shake it on the moon, one of them on the moon, and we're going to shake one down here. Which one costs more?
One on the moon.
What do the rest of you say? What?
The moon.
It costs more to shake it on the moon. Because on the moon, this paint is harder to shake because you have done all the work of getting it higher in the gravitational field of the Earth. The gravitational field of the moon is much smaller than the gravitational field of the Earth, so you've done some extra work on the paint by taking it away from the Earth. So it costs more to shake the paint on the moon than to shake it here. Now, on a black dwarf star, each of your bodies would weigh as much as one U.S. battleship. If your mother shook you by the shoulders, would you be harder to shake than you are here? Or easier?
Harder.
Easier. That's lower in the gravitational field, you silly goose. Not higher. We went downhill in the gravitational field. It's true you get heavier, let's say heavier to pick up, but easier to shake.
Yeah. Because you wouldn't be.
On the moon, it's easier to pick up, but harder to shake. And on the black dwarf star, it's harder to pick up. Well, it'd be quite impossible to pick you up on a black dwarf star, because I don't run around doing weightlifting with battleships. I don't do like that. But you'd be easier to shake. Have you all got this straight now?
Because you wouldn't be holding it back.
I'd be just as flat as you would be.
Well, is this shaking, the hardness of shaking related to the mass? Is it because of the...
Yes, the hardness to shake is related to the mass. If you were in a spaceship orbiting the Earth, and there was a ping pong ball and a golf ball, how could you tell which is which? They both float around the cabin. Drift around the cabin. They just drift around the cabin.
They resist changes of...
Yes, if you shake the golf ball, it'll shake like a golf ball. If you shake the ping pong ball, it'll shake like a ping pong ball. But you can't tell by looking at them. Well, you might say the golf ball has all those little dents in it. But you see, I have a ping pong ball that has all those little dents in it too. I found it at Clear Lake, on the shore of Clear Lake. I was so charmed. Ping pong ball and a golf ball with little dents. But you can tell right away by shaking it, because the golf ball will shake like a golf ball, and the ping pong ball will shake like a ping pong ball.
Because of inertia.
That's what we call inertia. How hard it is to shake is what we call inertia. That's also what we call energy. See, that's what we didn't know. That's what we didn't know. Now let me ask you something. Is there any such thing as the opposite of a dog? Is there any such thing as the opposite of a squirrel? One kid about your age says a crocodile. But you see, a squirrel and a crocodile are both alive. They have to have something in common in order to be a pair of opposites. Up and down or along the gravitational gradient. You see, if I said neither red, white, nor moist, then you're off beam, okay? Because moist doesn't fit there. Red and white might fit, but not moist, okay? It's not related to the other two things. But east and west is along the spin of the Earth. North and south is along the polar axis, okay? Up and down along the gravitational gradient. So like that. And male and female dogs can be opposite because they're both dogs. So in order to have a pair of opposites, we have to have two things that are the same in some way. Oh, I should have told you about that whole equation that I had on the board. X squared plus y squared plus z squared minus d squared. When I put that there for the University of California many years ago, 25 years ago or so, there was a man in the back of the room. It was a big class, I think more than 50 people were in the class, and they charged those people hundreds of dollars to get in there, and they kept all the money. Anyway.
Which reminds me.
Anyway, we can get a little bit of it. Anyway, so when I put that equation on the board, this man called out, he says, you can't put time under that radical like that with space. I said, did I tell you this before? No. He said, I said, you mean it's like adding apples and oranges? Yes, he said, it's like adding apples and oranges. Well, I said, when I went to school, they taught me that you couldn't add apples and oranges. But when I grew up, I found that you call it fruit salad, and you get by with it every time. I said, the S is for salad. You just can't call them oranges, and you can't call them apples. But if you have a general word, you're all right. So that's Einstein's word, I think, S for separation. Space separations, time separations, and mixed separations, all under one term. Now, how to get detoured on that? How to get detoured on that? What was I talking about before that?
Ability, inertia, ability to use different weights at different ends.
Oh, all right. So we had some detours, unwinding cuckoo clocks and things. So getting things farther away in the gravitational field, picking them up in the gravitational field winds them up. Letting them go unwinds them. Now with respect to electricity, pushing negative towards negative winds it up, and they want to get farther away. So if you have two electrons and you push them toward each other, are you winding them up? If you put a wrapper on them so they couldn't get away, do they weigh more there than they weigh farther apart? Yes, they weigh more there than they weigh farther apart. Now, if you had the charge of one electron, a great big, and you made it smaller, would you be pushing negative charge towards negative charge?
Yes.
Would you be winding it up? Yes, you'd be winding it up. And by the time you squeeze the charge of one electron down to the size of one electron, the work that you did on it is how heavy it is. There's nobody else in there. Now I'll say that again, because that was the most shocking piece of information that ever went across my ears at the university. Lawrence put it this way: if you push two electrical charges together that don't like each other, you're doing work at it. So if you take a great big electron and squeeze it down, you're doing work against it. And by the time you squeeze the electrical charge of one electron down to the size of one electron, the work you did on it is how heavy it is. That's what the mass of the electron is. I had always thought that matter consisted of little dirty particles with electrical charges. No, there are no little dirty material particles underneath this thing. There are not. Matter has fallen out of the physics. There are the electrical charges and the smallest of the electrical charges, and there's nobody else at home. All right, so we wind things up against gravity, and by the time we've done all the work to space things out like this, they're wound up to 500 nanomiles per pound. But let me put in some details so that you can see that I'm not pulling the wool over your eyes. If we drop something to a neutron star, didn't we talk about this before already? If we drop something to a neutron star, 1/10 of the energy of that thing would come out in a splash. If we drop an old-fashioned 10-gram marshmallow to a neutron star, the splash would vaporize Berkeley. A 10-gram marshmallow has 1 gram of kinetic energy when it arrives at a neutron star by free fall. When it falls to the surface of a neutron star, 1/10 of its energy is now in the form of kinetic energy, and 9/10 is still in rest energy. But 1 gram of energy is enough to vaporize Berkeley. Didn't I talk about getting a marshmallow off of a neutron star?
Yeah.
That's what I thought I did. We made this real strong cylinder with a little bung on it. So tuck our marshmallow in and fire the thing, and it just lifts off, okay? The energy that we get out if we drop it to the event horizon of a small black hole is 1/3 of the rest energy. And if we put all the matter of the universe back together into a black hole and dropped our 10-gram marshmallow in, all 10 grams would come out as kinetic energy. Now, if you see that you can do it going down that way, you can do it coming back out this way. In order to get a marshmallow away from all the rest of the matter in the observable universe, it takes 10 atomic bombs. Yeah.
Not sure I understand where the rest energy is stored.
Where the rest energy
If
is
your
stored,
marshmallow drops down,
what you call matter is simply stored rest energy. That's all it is. We don't have anything else here except energy. And this stuff, come up close please. There's lots of nice chairs up close here. They're just as warm as the stupid ones in the back. Here, look at these nice chairs. In fact, some of these guys can move over and you can sit together. Thank you. Where were we?
Are you saying that 1/10 of the mass of this marshmallow would cease to exist, or would be transformed in some way, and the other 9/10 would still be in existence, but wrapped around the
On a neutron star, the marshmallow would be easier to shake than it is here. That's if it didn't splash.
Mm-hmm.
We'll let it go down slowly. So it's still fine when we get it to a neutron star, but it's easier to shake.
Mm-hmm.
It's only 9/10 as hard to shake as it is here. If we take it to the event horizon of a small black hole, it's only 2/3 as hard to shake as it is here. If we take all the matter of the universe and put it into a black hole, it would be dreadfully easy to shake.
And
I
if-
think the energy would have gone away for rest energy, from potential energy. You see, in a swinging pendulum, we've got gravitational energy up here. It goes away to kinetic energy down here and then back again to gravitational energy. Is that clear to you all? The total energy is the same, of course. The total energy is the same. But it goes from one kind to another kind. So that's all that happens. The energy goes from one kind to another kind. Now, all through the universities, they tell you that matter can be converted to energy, and energy can be converted to matter. Just erase that. That is not what the equation says. In the swinging pendulum, we have E sub g plus E sub k is a constant. As this one plus that one is the constant. And that's not what this equation says. Now, all through the universities talk that way. And I can quote Jastrow and Dobson in a big book for university astronomers, for people after PhDs in astronomy and astrophysics. They've got written at the top of the page, E equals mc squared. And at the bottom of the page, they put in italics what they think it means. And I quote, syllable for syllable, the sum of mass and energy is indestructible. That's E plus m equals a constant. That's E plus m equals a constant. And that is not an equation. That is not what Einstein wrote. Einstein said what we call matter is just potential energy. In fact, we used to have a little movie at the Lawrence Hall of Science. You push a little button, and Einstein is there talking about it, and he refers to the equation in which energy is set equal to mass. But the physics at the universities, they do not teach it that way, they teach it this way. I don't care what university you go to, they'll teach it that way. I don't know a single university that does it any better. But you have to, what we test, you see, in our physics is the equations, not somebody's gut response. Everybody knows what the guts are filled with. So you have to take the equations the way they're written. Now, in my opinion, we don't have to do this one, that's for flatworms which have died, but you have to remember these two things. In my opinion, these are two of the things that you have to get under your belt if you're going to understand this universe. If you fail to handle one of these things, you have thrown in your sponge on understanding this thing. There are three things you're going to have to understand. The third one we haven't gotten to yet, but we'll get to it very soon. But this is what we call relativity theory. He has changed the geometry from 3D to 4D. This is three things, and this is one. Remember, we don't have to go bebopping around the room. We can always measure from one to the other. So we can simplify it to just one distance in space and one length of time. And we can simplify this one like this. And that's really very old physics. That's 1905, special relativity. And it's been tested for a very long time. Now let me tell you something about physics. You can't prove anything in physics. You cannot prove that all crows are black. All you can say is that you saw a heck of a lot of crows and they were all black. But if I have an orange one, you're dead. Got it? One and you're dead. So what we look for in physics is some way to see that our thing is wrong. The very first thing that Einstein did when he came up with these equations is to show where to find out that he's wrong. Now, Einstein did not become famous until 1919. By 1919, there was an eclipse of the sun, and Sir Arthur Eddington, and the war was over. They were afraid they were not going to be able to do the experiment. They wanted to take a picture of the sun when it's eclipsed, and see if the light from the stars has been bent around like this. So Sir Arthur Eddington did it in 1919. And then he gave a lecture under Newton's portrait in the Royal Society in London. And he said, the old bird blew it, and this Jewish kid's got it right. And Einstein was immediately famous. He was not famous until that lecture. They still thought he was a jerk. But he shows where you find out he's wrong, and he doesn't turn out to be wrong. Now you see, the scientists have this humility. Politicians don't have any such thing. They'll tell you where to find out that they're right. Never do it the other way. All right, now where are we? All right, now I can draw draw you a map of the physics of the last century. We have mass, energy, space, and what's down here? All right, now let me read from that nice book again. Where did I leave it? Thank you. Now what page is it? 84, maybe. Let me see. No, it's not 84. Oh, darn. Where is it? Ay, ay, ay. I've forgotten my page. See if I can recover this. Oh, maybe I can. Maybe I can. Yeah, you can all go get drink some water. You can all go change your water. Oh, darn, how could I forget what this was that I have to read to? Where is it? Well, darn, I don't remember. All right, ollie oxen.
Here it comes.
Is somebody in the job?
Yeah.
Okay, we'll wait. You all breathe easy. I won't get on your case to these apples.
May I ask something?
Yes, of course.
You mentioned energy is matter, but you said it differently before, like inertia, something like that?
Yes.
So I don't know.
Inertia.
Really.
Inertia means matters, let's see. Oh, it's page 71.
That's called inertia.
Didn't I read you? Didn't I read you page 71 already?
Yeah.
Didn't I read you 71 already?
Anything else on second?
Page 71.
I thought it was
No,
red and white
hang
and
on.
moist.
No, page 27 I need.
Betty Crocker's Christmas.
Page 27. I don't think I read you this. Maybe I did. Yes, I did. The physics before 1920. That's what we're going to talk about here anyway, the physics before 1920. You remember the other force that was about gravity, was called gravitation? This law was known and was very simple. Why things remain in motion and why, when they are moving, or why there's a law of gravitation was of course not known. Inertia is the statement that when they're moving, they want to keep moving. Now I'll give it to you in Newton's original Latin. Corpus omne perseverare status suo quiescendi, vel movendi uniformiter indirectum, nisi quatenus illura viribus impressis cogitur statum suum mutare. Bodies all persevere. In corpus, bodies. Omne, all. Perseverare, persevere. You can translate it yourself. Bodies all persevere in their states of quiescence, quiescendi, or of motion, uniform in direction, unless by forces impressed upon them they are compelled to change their states. That's inertia. If it's standing still, it wants to stay standing still. And if it's moving, it wants to keep moving in the same way.
But that's, for me, it doesn't have a difference to energy because it's like the same quality.
Yeah, never mind the same thing. It's the same thing, you silly goose. This is inertia, and this is energy. They're the same thing.
Ah, okay.
All right. go back a little bit. Remember I told you you can't have two things that are opposites unless they're identical.
Right.
Now we knew all along that energy and matter were opposites. We knew it all along. Energy is what makes things move, and inertia is what fights it. You have two pedals in your car. One to make it go when it doesn't want to go, and one to get it to stop when it's not willing. And unless you have them both in there, you do not have an operator's license. You have one to make it go when it doesn't want to go because it fights going if it's not going. And you have one to make it stop when it doesn't want to stop because it fights stopping if it's going. It's called inertia. It turns out that it's energy. There's nothing else in this universe except that. Everything that is here is made out of that energy. Everything that is here is made out of that inertia.
And before, shortly before you said also that matter is stored energy, like rest energy?
Yes.
And where's the other energy?
Rest energy is just inertia. You can have different kinds of energy, like the energy of a pitched baseball. It's not standing still until the catcher catches it. It weighs more while it's going. I know it's hard to weigh it while it's going.
Unless it's going away from you. I was just thinking about that Doppler effect.
Yes, if it was going away from you, it would weigh less. Going towards you, it weighs more. But if you look at it from the side, it weighs more. Now you see, if you have two spaceships passing each other this way. No, let's go back. Have another detour. We have two trains. One, the trains go here on the right side, don't they? This is not England. This is Canadian. Trains go on the right side. So we got a train going by 100 miles an hour this way, and a train going by 100 miles an hour this way, and we're on the station platform. We see this one going by 100 miles an hour. We see this one going by 100 miles an hour. How fast do they pass each other? 200. Anybody disagree with that? All right. Now we have two spaceships passing each other. We're still on the station platform, and one's going by 99% of the speed of light, and the other one's going by the other direction, 99% of the speed of light. How fast do they pass each other? Yeah, now you have to chuckle. Now you see how boo-boos you were. If you're wrong about the space vehicles, you're wrong about the trains. Is that clear? It's not that the Canadian Pacific will fault you for your mistake on the trains. They won't even notice it. It won't show on your salary. But NASA won't put up with it on the space vehicles. If two space vehicles, one passes us at 99% of the speed of light and the other goes the other direction, 99% of the speed of light, as seen by us, they pass, well, as seen by each other, each of them sees the other one going by at 99.995% of the speed of light. Now when they're coming toward each other, these people see those clocks whirling around like this, and they see those clocks whirling around like that. Now whose clocks are whirling? Now as soon as they pass, these guys see those clocks almost stopped, and these guys see those clocks almost stopped. Now whose clocks are stopping? There is no actual universe. Give it up. There is no actual universe. Space distances are not objective. Time separations are not objective. The only separation that's objective, that reads the same for all observers, is the space-time separation. And between the perceived and the perceived, it goes to zero. That's why the radiation goes to zero. If a photon can get from one event to the other event, then the separation between those two events is zero, and you don't have to say that any photon went there. The life history of all photons goes to zero. The life history of the photons goes to zero. I shouldn't say that, because they do have a time. They do have a time. They also have a distance, but the time and the distance are the opposite of each other. So the total separation goes to zero. It's really not that the life history goes to zero. I think we need some breather. You guys can pick on me for a while. Go on, pick on me for a while. Get it straightened out.
You were talking about mass being actually the work it took to
Yes, the
compress.
mass of the electrical particles is the work that it takes to make them that small. To make that much charge get small against its self-repulsion.
Okay, so then once they're small, they've got this incredible amount of energy, and yet
500 atom bombs per pound.
right, and yet they don't immediately expand.
They certainly don't.
So what is it that holds them together? If they have this incredible wanting to be a
Look,
part.
I'm not responsible for this bloody universe. I'm just describing it.
Well, somebody must have some ideas of what holds them together.
I'm just describing it. Anyway, we may worry about that later, but we're not quite ready even for that yet. Because very soon you'll see some other problems. I'm going to have to ask you, why doesn't the electron sit down with the proton? That may be related to the other problem. Why doesn't the electron sit down in the proton? Because the attraction between the electron and the proton is severe. If you had 2 grains of sand, 1 millimeter in diameter each of them, 30 meters apart, and one was made out of plus charges, and one was made out of minus charges, the pull between them would be 3 million tons. And that's the weight of 60 US battleships in a very large plastic bag. Now, if you had a big chain, you had one end fastened to some cliff, and you have this chain going over here, you see, and 60 US battleships hanging on the chain down here like a rosary, and you have 1 grain of sand fastened to the chain up here, and the other one fastened to the cliff over here, all the battleships would come up. And they wouldn't come up quietly either, because as soon as it got halfway over, it'll pull 240 battleships. Is that clearly wrong? And we're talking about the electron being right next to the proton, and you cannot overlook the attraction. Anyway, that's the homework for a few minutes from now. We're not right there. So get on my case about the stuff we've been through already. Yes.
But in the first couple of lectures, I got this idea about how empty space was. All the immense amount of
Yes, the
distance
universe is
between-
very lonely, very cold, and very dark.
Seems quite lively too, though.
It's quite what?
Lively.
Yes, it's quite lively.
Yeah.
Now, when I was a kid, they told us that matter was inert. You've probably all heard of this, that matter's inert? That's again cattle feces. Matter is inert. It moves by itself. What else moves? Matter moves. You drop something, it falls. Matter is inert. But you see, the ancients used to think that matter was inert, and we're inert, so we can move things around. So they thought that all these things happened because of the influence of the gods. The gods made the sun come up, and the gods made the moon go around, and the gods made the wind blow, and the gods made the rain come down. Okay? Because they were sufficiently jerky that they thought that they were the great movers. So everything else that moved had to be moved by somebody like them. So they had these gods to do it. Well, it turns out that matter is inert. It moves by itself. Yes.
Is all of electricity, the electricity you've been describing, is it all based on polarity like we know it, or what is electricity?
We're not ready for that yet. Just a few more minutes. Give me a few minutes. We'll get to it. What is electricity, and what is gravity, and what is inertia? We'll get to it, all right. It's going to be very soon. But it's hard to give it to you right away. You have to have a certain number of cubby holes to put it in. And right now we're building cubby holes. And anyway, but you see, electricity comes in 2 kinds, okay? But we see already that we have time against space is a pair of opposites, right? But space has 2 directions, the gravitational direction and the electrical direction. So gravity is the opposite of electricity. Gravity pulls, sucks, and electricity pushes, and they're both wound up to 500 atom bombs per pound. It's wound up against gravity by being spaced out, wound up against electricity by being spaced in. So this is a pair of opposites. But it's gravity against two directions of the electrical field, the plus direction and the minus direction. Don't you see? This whole business of pairs of opposites is 1 against 2 against 1 against 2 against 1 against 2.
So that creates all the motion and everything.
Yeah, everything's like that.
Okay.
The universe is really peculiar. We've got everything wanting to fall together, and everything wanting to fly apart, and everything wanting to stay still. I know, but that's how it is. Gravity wants everything to fall together, electricity wants everything to fly apart, and inertia says, knock it off. Well, it's not peculiar to the universe, it's the same with us. We fall in love, and then we get married, and then our freedom is gone. Then we get out, and then we're lonely, and then we get in. And all the time, leave me alone. We want to be totally in love, totally free, and totally alone. I remember one time in a movie, somebody asked the judge, what are the grounds for divorce in this state? Marriage.
So what
Yes?
keeps everything from reaching sort of a steady state? I mean,
What's that?
what keeps everything from reaching an equilibrium where?
There wouldn't be any equilibrium. There wouldn't be any equilibrium. And as I said, gravity wants it all this way, electricity wants it all that way, and inertia wants to knock it off. The universe is made out of frustration. That is the ingredient out of which the universe is made. It's not peculiar to us as people, it's peculiar to the universe.
So the change is constant.
What?
Change is constant.
Well, change is constant, all right, but it never gets anywhere. Gravity wants it all to fall together, and it doesn't succeed. Electricity wants it all to fly apart, and that doesn't succeed either. And inertia wants to knock it off, and that doesn't succeed. None of it succeeds. Now, we'll find out by and by why it doesn't succeed. But right now, we just have to take it for granted, because we see it just, we now have it now just as an observation that it's not succeeding. All of these contrary things are going on simultaneously, and none of them are succeeding. Anyway, now let me ask you some questions. I want to ask you about this. Now, in the, remember we were talking about the physics before 1920. We can still talk about the physics before 1920, or even farther back. It was taken for granted that the universe consists of real particles with real mass and real energy moving through real space in real time. Do any of you have any trouble with that? I think it's taken for granted in our guts that matter consists of real particles with real mass and real energy moving through real space in real time. Now, what happened to this picture when Einstein came? Einstein puts these two things in the same equation. And he puts these two things in the same equation. So this line is gone. Now, what about this line? Does that stay or not? Well, you could guess that it's not going to stay, huh? Well, it's not going to stay. Space-time is wound up against matter and energy, and matter and energy are wound up against space-time. If we didn't have the particles, we wouldn't have the gravitational field. If we didn't have the gravitational field, we wouldn't have the particles. The very existence of the particles depends upon their separation from each other in the gravitational field. If we didn't have the gravitational field, we wouldn't have the particles. But if we didn't have the particles, we wouldn't have the gravitational field. There's something wrong with this. I mean, you can see that there's something wrong with this universe. So this line is also gone. Now, when the lines are gone, the whole damn picture is gone. Because there's nothing you can define in physics except in terms of mass, energy, space, and time. If you look at the back of a physics book, when I went to the University of California, all the things that we talked about in that semester were listed in the back with their units. And they're all in terms of mass, length, and time. Everything is in mass, length, and time. Momentum is mass times velocity. Velocity is distance over time squared. No, not squared. But kinetic energy, 1/2 mv squared, so v squared is mass over energy, mass over time, velocity, distance over time squared. Anyway, they're all in terms of those things. So when the discrimination between mass, energy, space, and time has gone, we are left with a conundrum. Now the question is, what's under there? What is it that we see here? You see, the physics, really, if you look at the physics very clearly, very straightforwardly, it disappears into this conundrum. What's under there? All right, I'll tell you a story. I have all these funny stories. I've been to several summer scientific meetings of the Astronomical Society of the Pacific, but this one was in Pomona. And on the airplane on the way down, I was thinking, we haven't talked about the Big Bang, have we? Well, we'll have to talk about the Big Bang too. But on the plane I was going down, and I was thinking, the Big Bang people want us to believe that nothing made everything out of nothing. That is to say, they want us to believe that in the absence of the universe, there would be nothing. And I thought, isn't that unwarranted? So when I got down there, I was going to ask this question to William Kaufman. He was going to give a lecture the second day. But Alan Sandage gave such a lovely lecture, for a 2-hour lecture on the Hubble constant, really on the Big Bang. All the way through, he referred to the Big Bang as the creation event. And it was a very nice lecture, slow enough, careful enough, so that with a normal education, you can understand what the heck he's talking about. Not long, fast, and out of tune, like William Kaufman was the next day. So at the end of his, and all the way through, he referred to the creation event. The Big Bang is the creation event. So at the end, I got up and asked him, since we are now willing to talk creation event, and I wiggled my fingers like that, why must we assume that in the absence of a universe, and in the absence of space and time, there would be nothing? Isn't it unwarranted? To me, it's warranted that in the absence of time, we would have the absence of change. That's warranted. It could be nothing, but at least it has to be changeless. And in the absence of space, we would have the absence of dividedness and the absence of smallness. Smallness and dividedness are space problems, and change is a time problem. I said that leaves the possibility that behind what we see might be the changeless, the infinite, the undivided, which to me seems a long ways from nothing. That was the end of the conversation. He was not going to talk about that, and before I finished, some lady shrieked and clapped her hand over her mouth. Afterwards, I lived in her house on another years later, and I asked her, when I found out she was the one who shrieked, I asked her how come she shrieked like that. She said she could see that in this kind of audience of all these scientists, that question does not come up. Now, years later, Hawking, Stephen Hawking, you know Stephen Hawking, all doubled up in his wheelchair. He gave 3 lectures at the University of California. And the first one, they gave him Wheeler Auditorium, which held 750 people. And they gave him 2 other auditoriums for overflow, and they were filled up on the run. On the run, they filled up the overflow auditoriums. The next day, he gave another talk. They gave him the big auditorium, that's 1,200 seats, and the Wheeler Auditorium and the others for overflow, and they were all filled. The next day, I couldn't even get close enough to the campus to park my vehicle, and I missed the lecture altogether. All the halls were filled, and I could see the whole crowd out in the court. There was this whole crowd out in the court. Well, anyway, after his first lecture, I asked his custodian, if I may use the word custodian. Somebody has to see that you don't abuse him. So I asked him if I could ask him a question, and he said, yes, you may ask him a question, but make it answerable by yes or no. So after a little while later, after this man had finished and several other things happened, he was out in the sun in front of Wheeler Auditorium, and I got down on my knees, and it was very sweet. It was very sweet to be able to ask that man a question. And I said, I'm to ask you a question which is to be answerable by yes or no. I was very apologetic. I said, in order that my question could be answerable by yes or no, the question will be lengthy. And I told him that whole story about Alan Sandage and me at Pomona. And then I asked him, do you see any observational evidence whether what's behind what we see might be a zero, or whether it might be the changeless, the infinite, the undivided? Do you see any observational evidence as to whether what's behind what we see might be a zero, or it might be the changeless, the infinite, the undivided? He took the trouble to have his machine answer me, I'm not sure it's a meaningful question. That's his way to say no. If he saw the evidence that I see, he would immediately have said yes. He doesn't see it, so he says no. Gravity is the evidence that behind what we see is the undivided. There is no other explanation for gravity. Electricity is the observational evidence that behind what we see is the infinite. There is no other explanation for why the particles are electrical. And inertia is the observational evidence that behind what we see is the changeless. There is no other explanation for inertia. I think I already read to you from Feynman. He's very careful. Why there is inertia, we do not know. Why things fall together by gravity, we do not know. And Einstein said we cannot comprehend on theoretical grounds why matter should appear as discrete electrical particles. But when you look at the physics, this is what you see, which is so interesting. The electrical energy of an electrical particle would go to zero if and only if the size of the particle went to infinity. It's in the books as a number. The gravitational energy of the universe would go to zero if and only if the dividedness of the universe went to zero. It's also in the books as a number. Now comes this very... Do you need to chew this over for a while? Now you see, it would be one thing if the physicists at Caltech had an explanation for gravity, or for electricity, or for inertia. They don't have any explanation for any of these. All of them come out with this one little change in our point of view. And the change in the point of view is perfectly straightforward, goes right down straight through from the physics of 1905. Only half of the physics of 1905. I'll tell you another story, because we're not quite ready for this next half, but I'm going to tell it to you anyway. Feynman said someplace, I have it in print somewhere, but I don't have it with me. He said, there was a time, what the newspapers said, according to the newspapers, there was a time when only 12 people in the world understood relativity theory. He said, I don't believe there was ever such a time. He says, there was a time when only one guy understood it, because he figured it out and hasn't written his papers. But he says he doesn't think there was ever a time when 12 people only knew it, because once a paper was written, lots of people understood it in some way or another. But he says, I think I can safely say that nobody understands quantum mechanics. We'll get into that pretty soon. But you do have to chew this over. It looks to me as though there is an answer to what's behind that question mark. And it has to be the changeless, the infinite, the undivided. And now the question is, how did we get from the changeless to the changing? Because what we see is changing all the time. You must have noticed. What we see is changing all the time. And it's made of itsy-bitsy particles. Never mind the infinite. It's made of these itsy-bitsy particles. And it's all falling together. It all falls together by gravity, but it's all divided into atoms. Now, how did we get from the undivided to the divided? How did we get from the infinite to the finite? And how did we get from the changes to the changing, all in one swoop? You see, the problem is, how do you get from the changes to the changing without changing it? That's the problem, you see. How do you get from the changes to the changing without changing it? How do you get from the infinite to the finite without making it smaller? And how do you get from the undivided to the divided without cutting it up? Don't you see? It's a real hard problem. What we see is obviously changing finite and divided, and if you look at the physics, it runs you right into the changes into the undivided, or nothing will your will work. So the question is, how did we get from the one to the other? We mistook one for the other. If you mistake the changes for the changing, you don't have to change the changeless. You just have to do a boo-boo. If you mistake the infinite for the finite, you don't have to do anything to it. It's just a boo-boo. Now, this is my peculiarity. This is where I'm crazy, okay? But I'll stand by my ground. Now I have to ask you some questions. I'm suggesting that we've mistaken one thing for another. Now we have to examine the consequences of a mistake. What would happen, what would show up in our physics if it is a mistake? So, first I have to ask you, in terms of an illustration, I have to ask you 3 questions. Suppose it's dusk and we've mistaken a rope for a snake. Okay? We could do your friend for a ghost, but some of my friends believe in ghosts and they won't do it. I can't do it that way. I say they really believe in ghosts. So, mistaking a rope for a snake. I have to ask you 3 questions. If we've mistaken a rope for a snake, does the snake have to be different from the rope? Yes. Otherwise, it's not a mistake. If you take a rope to be a rope, that's a take, not a mistake. So we mistook the infinite for the finite. We mistook the undivided for the divided, the changes for the changing. So far, so good. They're all different. The next question is, if you mistake the rope for a snake, do you have to see the rope?
Yes.
Yeah.
Yes. Otherwise, you could mistake it for a Chevy.
But you wouldn't be able to tell anything about it afterwards.
It's the length of the rope that you see as the length of the snake. It's the diameter of the rope that you see as the diameter of the snake. So, that's why we see gravity, electricity, and inertia. Gravity is the undividedness, electricity is the infinite, and inertia is the changeless. It's not possible to make this mistake and not see those things. You can't mistake a rope for a snake without seeing the rope. It's the rope that you saw, damn it all, there's nothing else there. It's the rope that you saw. It's the changes, the infinite, the undivided, which we have seen, and we see it, and it shows through in what we see. It shows through in the boo-boo. All right, now I have to ask you one more question. No, I shouldn't ask you this other question yet. Well, I'll ask it to you anyway. If you mistake a rope for a snake, can you identify the snake? If you've mistaken a rope for a snake, can you identify the snake?
Yes.
No, of course not. All right, we'll get to that by and by. Now you should get on my case.
Well,
Yes.
on this thing what you just talked about, the snake and the rope there, the only way you'd be able to distinguish whether you've seen a rope or that you've mistaken a snake for a rope is to
No, mistake a rope for a snake.
is that you would have had to have known what a snake looks like.
That's what Shankara says. That's an old argument, and I say fiddlesticks. Because in the case of a rope and a snake, you could mistake a rope for a stick, the shadow of a power wire. There are a lot of mistakes you can make. You can even mistake it for a trail of urine. Okay? There are a lot of mistakes that you could make in that case, but in this case, there's not. If you don't see it as infinite, you have no choice. See it as finite. No choice. So that argument doesn't hold. Shankara was considered one of the best, most important philosophers that this planet has seen. Now, that's his argument, but I disagree with it. In this case, there's no choice. Schauber didn't see this quite the way I did. He didn't go to the University of California as a chemist. There's certain things which we can see easier than other people can see. But we didn't understand space and time in Shankara's time, but we do understand it since 1905. Einstein put it into the put time into the geometry where it belongs. Before that, it was three-dimensional geometry, and it didn't wash. Now we got a four-dimensional geometry. It'll go through any laundry that you choose.
So why do we experience, well, most of the time we're experiencing the universe or whatever and we're mistaken?
Correct. And you want to know why? Well, we'll get to that by and by. But we're not ready for that yet. But let me remind you that the way I have used the language here, there are two kinds of causation. Ordinary causation we've talked about for 2 nights already. Like if you drop something, gravitational energy becomes kinetic energy, and then the kinetic energy, when the stars shine, the kinetic energy goes to radiation, and the radiation picked up by the potato plant, and it makes potatoes, and we cut it up and make chips, and salt them and eat them. All right, all these things happen like that. Now that kind of causation is a happening in time, and it's covered by the conservation laws. The energy goes in is the energy that comes out. No energy comes out that didn't go in. Covered by the conservation laws. The momentum in is the momentum out. The angular momentum in is the angular momentum out. The amount of matter goes in is the amount of matter coming out. Okay? All those things we already know about. But this other kind of thing, which I'm talking about now, mistaking one thing for another, is not covered by the conservation laws. And it's not a happening in time. If you make milk into buttermilk, it's a happening in time. There's a shelf life on your buttermilk. You can look at this door. There's a shelf life on the buttermilk. But if you've mistaken a rope for a snake, it's not that you mistook the rope for a snake yesterday, and now there's a snake in the bedroom, and you're sleeping in the kitchen. It's not like that. It's something you're doing now. And the question is not, how did it happen? The question is, why the hell do you go on with it? And we'll have to talk about that by and by.
So it's the word, what the hell did we, what?
Why do you go on with it? Why do you, if you're mistaking a rope for a snake, the question is why, not why did it happen? It's the question is why are you making that mistake still?
Okay. Because you've got the infinite confused with finite, right?
What?
Because you've got the infinite confused with finite.
Yes, but the question is why do you go on with your confusion?
Well, I don't understand, like we've only brought it down to discussion anyway, so that we can look at it. But exactly where do we make that mistake?
That's what I'm not going to talk about yet. We're going to talk about why do we go on with that mistake, not why did we make the mistake. There's a reason why we go on with the mistake.
Because we insist on living finitely?
Yes, but I don't want to go on with that problem yet. That would get us too far ahead of the game. That's the question of what happened to us that didn't happen to the chimpanzees, and we're not really ready for that. We're still trying to figure out why the universe looks like it looks. Okay? We still haven't answered some real hard questions in the physics. Is it time for us to quit yet, or can we start on the next one?
It's about 10 to, so sure, go ahead and start if everybody's okay.
Go ahead and start it.
Is that okay
All
with
right.
everybody?
Why doesn't the electron sit down on the proton in the hydrogen atom? My friend tells me the picture of the hydrogen atom should be patented. Here's a proton. And here's an electron here, see? With an E minus, that's how chemistry writes it. The question is, why doesn't the electron sit down on the proton in a hydrogen atom? Remember, we have 2 grains of sand, 1 millimeter in diameter each of them, 30 meters apart. One's plus charges, one's minus charges. The pull is 3 million tons. And these are so close, you can't even show how close they are. And the question is, why won't the electron sit down? Like anybody else would, who is that much in love.
It has too much energy to sit down.
What?
It has too much energy.
Well, why doesn't it just dump it off? Like anybody else would.
Inertia?
What have you got, something to eat?
No, it just looks that way.
So this is it.
Why doesn't the electron sit down on the proton? Or if you like, why don't you fall through the floor? No, that's not like asking you why you don't drop dead, because we each get a chance to do that. But you don't get a chance to drop through the floor, and the question is, why not? Now let me tell you what the problem is. The nuclei of the atoms in the floor, if they were the size of garden peas, the electron clouds around them would fill football stadiums. So the floor is really like cotton candy. Remember the density that it goes to in a neutron star? 100,000 battleships in a 1-pint jar? This is a good vacuum, and you still can't fall into it. Don't you see? Why can't the cotton candy of your feet squish down into the cotton candy of the floor? Now you see, I was old, you know, before I found out this thing. I was old. I'd been all the way through the University of California, and nobody ever talked about these things. But you have to answer this for me. Why won't the electron sit down on the proton?
It wouldn't be a proton anymore.
What would it be? You're perfectly right. What would it be?
Another electron.
No. What would it be if the electron sits on the proton?
0.
No, it's not 0.
Neutron.
A neutron. It'll be a neutron. If the electron sits on the proton, it's a neutron. How long will a neutron live? Anyway, I'll give you an illustration of the difficulty, okay? Suppose this room is cleared of all the furniture, and all the lights are out, and all the street, there's a power failure in Kaslo, and the moon isn't out, and it's all totally dark in here, and we're all blindfolded, and we're all sitting around the wall, and each of us has a bag of ping pong balls. But somewhere out on this floor, there are 3 golf balls. We're all sitting around the wall with ping pong balls. Can we roll our ping pong balls across the floor and find out where the golf balls are?
Maybe, if you...
Yes, we could. Because if you're sitting over in that corner, and I roll one out this way, and I know which way direction I rolled it, and you catch it coming that way, and we know we can go in the other room where we have a light, we'll have a flashlight, and we'll make a chart. And you're in that corner, we'll draw the corner, we'll draw the room, and I'm here, and I rolled it that way, and you're there, and you caught it that way. The intersection of those 2 lines is a golf ball. Now if I roll it this way, and she catches it way over there, and it didn't change the direction, there's no golf ball. So we can find out where the golf balls are by rolling ping pong balls in the dark. Okay? Now we're going to change the scenery. We're still around the wall. This time we have bags of golf balls. And there are ping pong balls out in the floor. No. Why not?
Because if you hit one of the
Because the golf balls will spoil what we're looking for. It's like studying butterflies with hatchets. Like studying butterflies with hatchets. Oh, it was there a while ago.
Destroyed the butterfly before you could see it.
All right. All right. So there's a limit to what we can find out by a physical probe on a physical system, because the probe bugs the system. Now Heisenberg investigated that problem, and he came up with this very famous statement: what we cannot know about where something is, multiplied by what we cannot know about its momentum, can never be less than Planck's constant over 2 pi. I'll tell you what that means in English. What we cannot know about where something is, multiplied by what we cannot know about what it's doing, can never be less than this little guy, which we don't have to know anything about. Now, Planck's constant is a constant, and 2 is a constant, and pi is a constant, so this doesn't get bigger or smaller. This one has its own size, and it stays its own size all the time. This one multiplied by this one can never be bigger than this one. Smaller, no, it can never be smaller. It has to be either bigger or equal to it, it can never get smaller. The uncertainty can never get small. It can get as big as you like. Is that okay? The uncertainty can get as big as you like, but it cannot get small. So if one of them gets small, the other one has to get big. Is that clear? All right. Now I'll give you an example. I used to live on a one-way street in San Francisco, Bush Street, where the lights are set for 30 miles an hour towards town. If you know that a car went through one light, what do you know about its speed? Nothing. If it goes through 10 lights, what do you know about its speed? Well, it's not too far off 30. If it goes through 100 lights, what do you know? It's very close to 30, but you don't know where the hell it is. Okay? You can know one of these things or the other.